I'll turn it over to Paul Gorse, who will moderate the second talk.
Excellent. Thank you, Dan. For our second talk, again, I'll be monitoring the chat slice if you want to interject your questions that way. We have J.D. Quigley from Cornell, who's going to speak on the algebraic slice spectral sequences. Take it away, J.D.
All right, thanks. So first, thanks to the organizers for the invitation to speak here. I think I went to like 15 Midwest topology seminars in a row as a grad student. So it's really an honor to be talking at one. Okay, I'm going to turn off my video because I have to put this thing horizontal to write on it. So I'm going to be talking about algebraic slice spectral sequences. This is joint work with Dominic Culver and Hannah Jiakong. And for people who want to follow along, you can access the slides by following this link down here. This will be on every slide. You can also read about more stuff in this archive preprint. Okay, so a quick overview of the talk. I'm going to start with motivation and main theorems. So our motivation is equivariant and motivic homotopy theory, and in particular, some particular spectral sequences that we'll use to calculate in those areas. So I'll give 4 main theorems, and I'll break down those 4 main theorems in various levels of detail. And then if there's time, I'll talk about some future work that we could do with these tools. Okay, so I'm going to start with the motivation. So our first motivation is equivariant. So many people have probably heard about the Hill-Hopkins-Ravenel slice spectral sequence. So we start with a G spectrum E, and Hill-Hopkins and Ravenel introduced this HHR slice spectral sequence, which starts with the equivariant homotopy groups of some G spectrum associated to E, and converges to the equivariant homotopy groups of E. For this talk, it's not actually so important that you know how this spectral sequence is constructed, or really what these objects are. Let me just tell you 2 examples to maybe motivate studying this spectral sequence. One of them, which is maybe the most famous, is Hill-Hopkins and Ravenel used this spectral sequence to resolve the Curvaire invariant 1 problem at the prime 2. Another more recent application of this spectral sequence is in chromatic homotopy theory. So there's a lot of work by Beaudry, Hill, Shi, Wang, Xu, and Zheng in this area. And of course, there are a lot more names that I should mention, but I'm forgetting. So you can use this spectral sequence to access chromatic computations at large heights, which is pretty cool. For the purpose of this talk, I want to just mention 2 examples of computations that have been done. Both of these examples, I'll work with just the cyclic group of order 2, C2. So the first one is the Hill-Hopkins-Ravenel slice differentials theorem. So they study this spectral sequence, and in particular, its differentials for real cobordism. And if you localize at a prime, real Brown-Peterson homology. So that was used in this Curvaire invariant 1 work. Another result, which is sort of the pioneering result in this area, is a result of Duggar, which I think was one of the first complete analyses of this spectral sequence. So he worked with the group C2 and studied this spectrum KR, which is a connective version of Atiyah's real K theory. So these are the 2 examples that I'll come back to in a minute. So along with equivariant motivation, we also have motivic motivation. So I'm lucky to be speaking second, so everyone now has heard a lot about this category SHK. So a whole bunch of people worked on a motivic version of the slice spectral sequence. So given a motivic spectrum E, there's this thing called the effective slice spectral sequence, which starts with the motivic homotopy groups of some spectrum associated to E and converges to the motivic homotopy groups of E. So there are a lot of applications of this spectral sequence. I just want to point out one. So Rundig, Spitzweg, and Östver studied this for the case where E is the sphere spectrum. So these are the motivic stable homotopy groups of spheres. And they use the spectral sequence to relate these motivic stable homotopy groups to certain variants of algebraic K theory. So things like Milnor K-theory and Hermitian K-theory. So we're also motivated to study this spectral sequence. I'll mention two examples that I'll come back to in this talk. The first one is work of Yagita, which studies this spectral sequence for algebraic cobordism, which we saw in the previous talk, as well as p-local version, which I'll call algebraic Brown-Peterson homology. And then there's a whole bunch of people who studied this in the case where E is non-connective algebraic K-theory, KGL.
JD, just quick interjection from the chat. Dan points out that Dan Duggar's work, Dan Isaacson points out that Dan Duggar's work was pioneering. It was way before many of the other things and really got many of these ideas going.
Sure. Yeah, thanks for mentioning that. So yeah, Duggar's work came much before HHR. Maybe it's the motivating example behind their work. Okay. So we have these two different motivations, equivariant and motivic slice spectral sequences. What I'm going to tell you about is how we can study these spectral sequences with some new tools. So now I'm going to say some of our main theorems. From now on, I'm going to implicitly complete everything. You can do this at other primes, but I'm just going to stick to the prime 2 today. So our first result is a C2 equivariant result. So what we can do, first of all, is we can completely understand the Hill-Hopkins-Ravenel slice spectral sequence, or the HHR SSS, for connective algebraic K-theory. So this is recovering that result of Duggar. We can also understand some of the differentials in the HHR slice spectral sequence for real Brown-Peterson homology. So this is recovering part of the HHR slice differentials theorem for the group C2. And finally, we can study some connective version of real Morava K-theory. I'm sure this has been studied, but as far as I know, this hasn't appeared in the literature. So maybe someone can correct me if I'm wrong, though. So maybe this is new. Okay, so we can recover a lot of these results with our techniques. And theorem A, which is this equivariant result, actually comes from a motivic result, which I'll call theorem B. So here I'm just going to stick to certain base fields, but again, we can do this more generally. So using our techniques, we can completely understand the effective slice spectral sequence for connective algebraic K-theory. So this is what appeared in the previous talk as well. Algebraic Brown-Peterson homology, and connective motivic Morava K-theory. So maybe one thing I'll point out is that this KGL here is a motivic analog of KR, BPGL is the motivic version of BPR, and K of N is a motivic version of KRN. So we're going to understand the effective slice spectral sequence for these motivic objects, and then use some cool results of Drew Hurd to infer the results over here. And now in the Midwest, I think generally we've been focused on the real numbers and the complex numbers a lot of the time. But just as an example of what we can do with this technology, you can work over other base fields. So over finite fields, we can also understand the effective slice spectral sequence for some of these motivic spectra. Okay, so those are like the computational applications that I'll come to towards the end. Now I want to tell you, how do we do that? So how do we understand the effective slice spectral sequence? So for now, I'm just going to restrict to the case where my base field has characteristic 0. Again, you can do it more generally, but I'll just make my life easy now. So our main computational tool is this theorem C. So let's say that E is a motivic spectrum, which satisfies this condition in red. For now, I'm just going to ignore it. Then there's a square of spectral sequences of the following form. So let me try to walk you through this. So down here in the bottom right-hand corner, I have an effective slice spectral sequence, or at least some variant of it. So in our work, we study several variants of the effective slice spectral sequence. I don't want to go into what those variants are. So when I'm talking about more general versions of this thing, I'll just put a hat here. And when I want to talk about the actual effective slice spectral sequence, I will remove the hat. So anyway, morally speaking, this is what we want to study. Now, in the Midwest, I think I was trained to believe that the Adams spectral sequence is maybe the most friendly and interesting spectral sequence in the world. So the other two sides, here and here, these are Adams spectral sequences in the motivic setting. So we have the square with the thing we want to study, the effective slice spectral sequence, two friendly Adams spectral sequences. And then finally, there's this titular spectral sequence, the algebraic effective slice spectral sequence. So we build this square, and the idea is that maybe we can understand these Adams spectral sequences, and maybe this algebraic object is easy to understand, and that'll tell us about the spectral sequence we want. Okay, so an obvious question at this point is, well, one, what does it mean to be algebraically sliceable over K? But maybe more importantly, before you even know what that is, are there actually examples of motivic spectra that are algebraically sliceable? So for that, here's our last theorem I'll talk about today. We proved that the following motivic spectra are algebraically sliceable. So we have connective algebraic K theory, truncated Brown-Peterson homology, connective Morava K theory, and this spectrum called KQ. So let me just say something about non-examples, and then I'll tell you what these correspond to in the classical setting. So all of these things we can apply this comparison square to, but there are definitely examples where we don't think we can apply it. So some of our non-examples of algebraically sliceable spectra are the infinite Brown-Peterson spectrum, BPGL. So this is like a p-local version of MGL, which we saw in the previous talk. Another non-example is the motivic sphere spectrum itself. So unfortunately, we can't use this to, say, understand the slice spectral sequence for motivic stable homotopy groups of spheres directly. Just to try to convince you that these are sort of common spectra to study, let me write down their corresponding classical spectra. So KGL is like a motivic version of connective complex topological K theory. BPGLN is like truncated Brown-Peterson homology. KN is, well, KN, connective Morava K theory. And this KQ, which is called the very effective cover of Hermitian K theory, is like an analog of little KO, so connective real topological K theory. And then of course down here we have BP and the sphere. Maybe one thing that I'll point out, because maybe we have some chromatic-minded people in the crowd, all of our examples of algebraically sliceable spectra are concerned with chromatic height less than infinity. So we have something like 1, n, and 1 here. Our non-examples concern all chromatic heights, so what you might write as height infinity. So there's an interesting connection between the chromatic height of the object of a motivic spectrum and whether or not it's algebraically sliceable. I'll maybe say a word about this in a few minutes. Okay, so here's the plan for the talk. I'm going to first tell you about the comparison square. So basically, what does it mean to be algebraically sliceable, and how do you, and what are all the spectral sequences in that square? Second, I'll prove to you that KGL is actually algebraically sliceable, so it has a comparison square. Then I'll use the comparison square to understand the effective slice spectral sequence for KGL. And then using results of Drew-Hurd and a little bit of computation, I'll explain how this motivic result, theorem B, implies theorem A, recovering Duggar's results. All right, so that's the plan. So first I want to talk about this comparison square. So let me just put it back up here. So here's what we want to study is the effective slice spectral sequence. I'll tell you about that first. Then I'll remind you about Adams spectral sequences. And then once we have those, I'll tell you about the algebraic effective slice spectral sequence. Okay, so let's start with the effective slice spectral sequence. And again, here I'm putting hats over everything. So for people that know what this thing is, this hat could mean effective slice spectral sequence. It could mean very effective slices, or it could mean some other variant. But the point is that we have some effective slice tower with some version of connective covers at the top, and then some sort of slices or cofibers along the bottom. And anytime we have a tower like this, we obtain a spectral sequence, which starts with the homotopy groups of the filtration quotients, or these slices, and converges to the homotopy groups of E. So I want to give some notation here, or terminology. So this FQ, I'll refer to as the qth effective cover of E. And I'll refer to SQ as the qth slice, or maybe the qth effective slice. And maybe one thing I should point out, if it's not clear, is that each of these is supposed to be a cofiber sequence. So SQ is the cofiber of FQ plus 1 mapping to FQ. All right, so that's our effective slice tower. And in the usual way we obtain a spectral sequence, one thing I want to convince you of, if you haven't seen this before, is that this effective slice tower is really like a Postnikov tower, but in the Motivic setting. So let me give you an example, which is the one that we'll work with for the rest of the talk. So I want to study this effective slice tower for KGL, which is this connective algebraic K-theory. So the way KGL is defined is as an effective cover of periodic algebraic K-theory. So I'll just tell you the answers to start. So if you take the qth effective cover, you get a suspension of KGL. If you take the qth slice, you get a suspension of the integral Eilenberg-MacLane spectrum. If you work with non-negative slices, and you get 0 otherwise. So the tower that you end up with looks like this down here. So you have KGL, suspension to 1 KGL. The cofiber is a copy of Z. And then if you go back, you have a 4-fold suspension, 2-fold suspension of KGL, and then you get a 2-fold suspension of HZ, and so on. So this should look familiar. I see a chat here. Oh, I'll let someone else answer that question. I'm not sure. Oh, well, actually, I can answer the question in the chat. So you can also go to my webpage, and you might be able to just view the slides there. So they're just posted and called slides somewhere. Oh yeah, thanks, Gabe. Okay, so I want to talk about this example and why it's like a Postnikov tower. So what's the classical analog of what's going on here? So then I would work with E equals little ku, and the analog of the effective cover is the connective cover. So that's the classical top line. Now there's a slight mismatch in indexing. So this qth effective cover is really like a 2qth connective cover. And if I take that connective cover of Ku, I just end up with a suspension of Ku again. And now what are these slices? Well, I guess it's 2Q to 2Q plus 1 of little ku. And Bott periodicity tells us that this is either a suspension of Hz for the same bounds on Q, or it's 0. I guess I can write these in. So let me see if there's space here. So I could write the Postnikov tower for Ku, and it should look extremely similar to what I've written for KGL. So let me just fill that in here. Okay. So what I want to communicate with this example is that this effective slice tower, or some of its variants, is really like a Motivic version of the Postnikov tower. So even though it may be somewhat new, and some of the objects we're considering may appear to be pretty new, it does feel like something classical. Okay, so this is the spectral sequence we want to understand. So I've told you about this side of the diagram. Now I'll tell you about the Motivic Adams spectral sequence. So from now on, I'm going to start using H. Well, let me show that. So I'm going to start using H to denote mod 2 homology. And I'll write H bar to be the cofiber of the unit map from the Motivic sphere spectrum to HF2. So just like in the classical setting, so maybe some people have seen this before, I can form what's called a canonical Adams resolution for any Motivic spectrum E. So I start with E up here, and the idea is to resolve it by mod 2 homology. So I start by recognizing that E is equivalent to E smash the sphere spectrum. Now I can apply my unit map from the sphere to H and the identity on E. So maybe I'll call this I. If I took the cofiber, I would get H bar smash E. But if I take the fiber, I turn my triangle and I introduce a desuspension. So that's where that suspension -1 comes from. Now I can play the same game. I realize that this thing is the same thing smash the sphere spectrum. And again, I can apply my unit map, smash the identity on the second two factors, and then take the fiber, then smash with the sphere, take the unit map, take the fiber, and so on. So the resulting resolution is called a canonical Adams resolution for E. And anytime you have such a resolution, you get an Adams spectral sequence. So the exact grading is not so important for this talk. I'll tell you more about this object and this object. So this is the dual motivic Steenrod algebra, and this is the motivic homology of a point. So those are not so important right now. Maybe I can indicate why we're seeing an Xed group though. So if you look at the filtration quotients, so you would want to apply homotopy to the filtration quotients to figure out the E1 page. And we see here that we have like H bar to the 0, H bar to the 1, H bar squared. We would have H bar cubed over here. When we apply homotopy, we're getting something that looks like a Kobar resolution. So what you can do, or what turns out to happen, is you identify the D1 differentials with Kobar differentials. And so your E2 page should look something like some derived functor like Xed. So if you haven't seen it before, maybe this Xed shouldn't be too mysterious. Anyway, you have this Motivic Adams spectral sequence. It starts with Xed groups with the homology of E as one of the inputs, and it converges to Motivic homotopy groups of E. Okay, so hopefully that rings a few bells for people who've seen the classical Adams spectral sequence. So now I've told you about the effective slice spectral sequence, and I've told you about the Motivic Adams spectral sequence. And of course, these are converging to the same things after I complete. So I can form the bottom two sides of my square like so. Now the next thing to realize is that the input for the effective slice spectral sequence is a bunch of homotopy groups. And while we could maybe, so how are we going to access these homotopy groups? Well, let's just use an Adams spectral sequence. So we can put in a third side to our square by putting in a big direct sum of Motivic Adams spectral sequences. So that's where this side comes from. Now the last question we have is how do we fill in this last side of the square? So how do I get a spectral sequence that goes from x of the slices to x of e. Okay, so I've just rewritten what I want here. I want this spectral sequence that goes from x of the slices to x of e. And I want this to be compatible with the effective slice spectral sequence, the one in homotopy. So I want to produce this spectral sequence using the effective slice tower that I wrote down earlier. But now there's a problem, right? So I want to hit this tower with this functor, x over the dual Steenrod algebra from homology of a point into homology of blah. And the problem is that unlike when I apply homotopy, which sends cofiber sequences to long exact sequences, I'm hitting each cofiber sequence with a composite of two functors. So I'm first applying mod p homology, which would send a short exact. Oh, I have no idea what's going on. Sorry about this. Interesting. Okay. Let's just pretend that none of this happened. Okay. Sorry about that. Anyway, so I hit this with mod p homology. And this is going to send a short exact sequence to a long exact sequence. But I can't feed a long exact sequence into X and get a long exact sequence. I would just get something weird. So I need to impose a condition on E to force these long exact sequences to split, or rather to ensure that they split into short exact sequences. So again, I'm going to apply homology to each of these cofiber sequences in the slice tower, and I'll get a long exact sequence. But I only get a long exact sequence in X if this splits into short exact sequences. So that's what will make our definition. We'll say that our motivic spectrum E is algebraically sliceable over K if each of these long exact sequences splits into short exact sequences of this form. So it goes from the homology of the qth effective cover to the homology of the qth slice to the homology of the q plus first effective cover. And we require this for each possible cofiber sequence in our slice tower. All right, so once you have this condition imposed, you can hit this short exact sequence in homology with X and get a long exact sequence. You splice those together and you get this spectral sequence, the algebraic effective slice spectral sequence. So that's our theorem C, that if your E satisfies this one extra condition about the homology of its slice tower, then you get a square of spectral sequences, starting with X of the slices and converging to the homotopy of E in two different ways. Okay, so I want to tell you about an example, or at least convince you that some familiar motivic spectra are actually algebraically sliceable, meaning that we actually get a comparison square for them. So I wrote this down earlier. Here's the slice tower for KGL. So I want to prove that the homology long exact sequence for each cofiber sequence in this tower splits into a short exact sequence. Sorry, I don't know what's going on with my mouse. Okay. I think I'm not allowed to like scroll over that way. Sorry about this. Okay. I think as long as I stay away from the scroll bar, we're okay. Okay, sorry about that. I'm gonna just keep the mouse to the left from now on. Okay, so again, I want to show that the homology long exact sequence for each cofiber sequence splits into a short exact sequence. So here's a sketch of the proof. So you start with your cofiber sequence and you hit it with homology. Now, this homology long exact sequence is special, and actually this cofiber sequence is special because the map from the q plus first effective cover to the qth effective cover is multiplication by the bot element. So just like in the classical setting, we have a bot element in the motivic setting. And one thing that you might know from the classical setting is that the homology of the bot element is 0. So what this tells us is that this map is 0 and this map is 0. So our long exact sequence splits into a short exact sequence of this form. Okay, and that's all we needed to prove, right? So now we know that KGL is algebraically sliceable. Maybe I'll just comment that the proof that we've given here just uses the fact that beta induces 0 in homology. And that's why we have these other chromatic examples. So in those other examples, it basically boils down to showing that realizing that this map is like multiplication by Vn. Okay, so now I've told you that KGL is algebraically sliceable, which means we can study the comparison square for it. So now I want to prove for you theorem B. I want to show you how we can understand the effective slice spectral sequence for KGL over the real numbers. So I've written the spectral sequence here. It starts with the R-motivic homotopy groups of KGL, and it converges to the of the slices of KGL, which were these suspensions of H-Z, and converges to the R-motivic homotopy of KGL. So of course, we're going to do this using our comparison square. And okay, here's what we want. And the effective slice spectral sequence seems mysterious, so the program is understand these Motivic Adams spectral sequences and maybe the simpler algebraic effective slice spectral sequence. Okay, at this point you might be like, well, this seems like a terrible idea because this is just one spectral sequence, and now you're saying I have to understand 3, so that's dumb. But luckily, there's a proposition of Hill that tells us that all of the Motivic Adams spectral sequences in this square collapse. So Hill showed that both of those collapse, and the proof is actually not so hard. So if there's time, I'll try to explain how these X groups are calculated. And then the point is that this Motivic Adams spectral sequence has a Leibniz rule. And once you know the E2 page, you see that all of the generators are permanent cycles. So that's why this collapses. So it's not really any harder than calculating the E2 page. Okay, so Hill has told us that this collapses and this collapses. So to understand what happens in the effective slice spectral sequence, I really just have to understand what happens in the algebraic effective slice spectral sequence. So this is the important thing, is we've reduced our homotopical problem over here to a problem in Ext. All right, of course, how are we going to understand Ext except by using another square? So here's what we want. We want to understand this amber algebraic effective slice spectral sequence over the real numbers, but that might be too hard also. So instead, we can work over the complex numbers. And I'll explain in a second why working over the complex numbers is easier. And then we can study the analogous algebraic effective slice spectral sequence. And then we need a way of passing from complex motivic computations to real motivic computations. And we'll do that using another spectral sequence called the Rho-Bockstein spectral sequence. And I'll explain what this is now. Okay, so our goal here is to calculate Ext over the dual motivic Steenrod algebra from the homology of a point into the homology of our spectrum. So what I want to remind you of is what is the homology of a point, classically and motivically, and what is this dual motivic Steenrod algebra, or at least how might we think about it? So here's the classical result. I guess this should actually just be singly graded, but the classical homology of a point is just the coefficient ring, it's F2. What about the dual Steenrod algebra? Well, Milnor computed this for us, and it's this infinitely generated polynomial algebra over the ground ring. Okay, so that's not so bad. And we know how to understand Ext in this case. At least in many cases, we know how to understand these Ext groups. When I go to the complex motivic setting, things only get a little bit harder. So my ground ring, instead of being just F2, is now F2 adjoins some polynomial generator. And then the dual motivic Steenrod algebra over the complex numbers at least as an algebra, is just obtained by tensoring up to this larger ground ring. What I want to say here is that computations in the C-motivic setting are actually not much harder than classical ones. And the reason is because this ground ring is central in the complex motivic case. So even though you're putting in this new generator tau, you're actually not forced to do much more work. It kind of just comes along for the ride a lot of the time. In contrast, in the R-motivic setting, we again just have to add one more polynomial generator called rho, but now I've put some scare quotes. So morally speaking, the dual R-motivic Steenrod algebra is again just like the complex one, but base changed up to this larger ground ring. But the problem is that now rho is not central. So instead of working with a Hopf algebra, we have to work with a Hopf algebroid in the R-motivic setting. And that sounds hard. So Hill had this great idea to study what's called the Rho-Bockstein spectral sequence. So the idea is, how are we going to compute R-motivic X down here? Well, we might use a Kobar complex with entries that are like the coefficients here, the ground ring, and this dual motivic Steenrod algebra. But understanding that Kobar complex is hard because of this non-central element rho. So what you do is filter your Kobar complex by powers of rho, and then in the associated in the filtration quotients, you'll have rho equals 0. So the filtration quotients, you'll get something that looks like the C-motivic setting. And in fact, you do get a spectral sequence out of this. So your spectral sequence starts with these somewhat easier to understand complex motivic X groups. You would join this polynomial generator rho. Then your spectral sequence says, well, what is rho actually supposed to be doing? And after you figure that out, you've computed real motivic X. So this is the Rho-Bockstein spectral sequence. So now I guess I've told you this is what we want. I'll claim that this C-motivic algebraic effective slice spectral sequence is easy to understand. So really what we need to do is understand these Rho-Bockstein spectral sequences. And then I'll tell you why this is easy at the end. Okay, so how do we understand these Rho-Bockstein spectral sequences? So here's the two that we want to understand. On the previous slide, I had SQ of KGL. But just as a reminder, the slices of KGL are just suspensions of HZ. So to understand that Rho-Bockstein spectral sequence, I really just have to understand what happens for Z. And then the other one I wanted to study was the Rho-Bockstein spectral sequence for KGL. Okay, so here's the E1 pages. This is what we're computing. Now, if you believe all of the stuff that I mumbled 2 slides ago, then computing the E1 page of the Rho-Bockstein spectral sequence is not so hard. So that amounts to computing these complex motivic X groups, but those are basically the same as classical ones with just tau adjoined. So just to illustrate this, classical X of HZ would give me F2 adjoined V0. I have to insert this tau because I'm working over the complex numbers, and then I have a rho because it's a Rho-Bockstein spectral sequence. Similarly, KGL is like a motivic version of little ku. X of ku gives me F2 adjoined V0, V1, tau because I'm working over the complex numbers, and rho because it's a Rho-Bockstein spectral sequence. So I can calculate the E1 page of both of these, basically by classical results. And then you have to calculate differentials. So in both of these spectral sequences, there are D1 differentials, which are generated by a differential D1 of tau equals rho V0. In the bottom spectral sequence, the one for KGL, there are also D3 differentials generated by D3 of tau squared equals rho cubed V1. And then after this, both spectral sequences collapse. So I don't want to go into the full computation for the sake of time, but let me just try to explain where this D1 differential comes from. So let's look at the Rho-Bockstein spectral sequence for Hz. So I've rewritten the spectral sequence here, and this is the differential that we want to produce. So where does this come from? Well, I told you that the Rho-Bockstein spectral sequence comes from some filtration of a Kobar complex. So where's this differential coming from? It's a differential in the Kobar complex. So it's the left unit in our Hopf algebroid minus the right unit in the Hopf algebroid. So Voevodsky computed these in his power operations paper, I think. So you can just take those formulas, figure out what the answer is. You get rho tau 0, and rho tau 0 represents rho v0 in Ext. So this is the only little computation that you actually have to do that's new here. So that gives you your D1 differential, and then the spectral sequence collapses at E2. Okay, so I don't expect everyone to follow what's going on at this point. I think the point that I just want to hammer home is that these differentials come from really simple calculations. This is just adding and subtracting at this point. For KGL, it's a similar story. So you have the same D1 differential, and then you have to prove a D3 differential. This also comes from a really simple algebraic computation. So I'll just put it here to illustrate that it's basically one line. But anyway, you do this computation, you get this D3 differential in the Rho-Bockstein spectral sequence, and then the thing collapses. So okay, my point here is this Rho-Bockstein spectral sequence, which I guess I should also mention, all of these Rho-Bocksteins were computed by Hill in the paper where he introduced this thing. So what I want to say is these are not so hard to understand. So okay, what did we learn? We learned that there's D1 differentials in this left-hand side, the spectral sequence for the slices. And we learned that on the right-hand side, there's D1 differentials and D3s. And actually, we noticed that the D1 differentials here correspond to the D1 differentials over there. So we really just have to understand what's happening in this blue top algebraic effective slice spectral sequence. And then once we understand that and these D3s, we'll understand what happens in the amber one, because that will have to account for all of those differentials. So now let me tell you about the blue algebraic effective slice spectral sequence up here. So here's what it looks like. But now we're starting with complex motivic Ext groups, and we're converging to complex motivic Ext groups. And I've told you already, these are basically just classical things with tau floating around. So let me just say that the left-hand side works out to be F2 adjoin V0 tau rho, and then I introduce an X here. X here. And X is supposed to tell you about Q. So which summand you're in. In the right-hand side, so what we're computing, this is something I already wrote. You have F2 adjoin V0, V1, tau, and rho. So there's an obvious isomorphism between these, right? Just send X to V1. And so the left-hand side is isomorphic to the right-hand side. So this spectral sequence collapses. So what have we learned? We learned that there were D1 differentials and D3 differentials on the right, D1's here, and this does nothing. So what do we conclude? So let me just fill these in. So these D1 differentials account for each other. So there has to be some DR differentials that account for these D3s. And it turns out that they're D1 differentials. Okay, I think I have 1 minute left, so I'm just going to rush through here. So what's the conclusion? Those D3 differentials in the Rho-Bockstein spectral sequence give us D1s down here. Both of these collapse. And because we had basically the same filtration for the algebraic and normal effective slice spectral sequences, we obtain D1 differentials down here. More importantly, we just had to do these algebraic computations to deduce this D1. So maybe that's the moral of the story. Okay, I see it just hit 245, so maybe I'll just quickly mention that using this cool result of Hurd, we produce a D3 differential in the HHR slice spectral sequence. We do a few computations with some elements that maybe the experts will know what these mean. And then there are some possibilities here for future work. Okay, I'll just end there. Thanks.
Hey, thank you, JD. It's a nice contrast with the first talk to have somebody really compute something, and first talk have something quite elegant as well. I think now you'll be in a breakout room, and